The Elements, a visual exploration of every known atom in the universe. Usually for these kinds of books, I create literally just one video. And then later, I just forget about the whole book. But Elements itself is very unique. In fact, it's kind of so unique that my dad himself got interested into this and took a few photos of it for work, even though he's never heard of the book before. Regardless though, one video will not do justice towards the elements, so I will create several videos, as many as it takes. Let's do some math real quick. Point 6, make sure my calculations are correct. Yep, they're correct. Round that up, 24 videos, including this introduction video, 25. It will take about 25 videos. Each of them will be at least 5 minutes, except for the first video, which will be at most 10 minutes. To go ahead and give this book justice, mainly because there is 118 elements currently, and this book was written in 2009, which is 16 years ago. And so for the first video, we will go ahead and talk about an introduction towards the elements and the periodic table. Oh, and no reference towards THEODORE Gray here. He has never helped me. I've never seen him in my life. And starting with the humble hydrogen all the way to the few second lasting organeson, we'll be traveling the whole span of the periodic table. And with all that, we will be able to hopefully get through an entire field of the periodic table itself. And so in the end, we'll just need to do like 25 videos. Alright, but first, you need to know what the periodic table is. The periodic table, as the name suggests, it's a table. Not the table like the one I'm using to record this video on. Not the one made of wood or metal. It's the one that's a graph. It's basically a graph. Probably more accurate to call it the periodic graph. But it's been called the periodic table, so we'll call it the periodic table. It's a list of the elements, except instead of writing them out as 1, 2, 3, 4, 5, 6, no, that will take too long, and it will be a very long list. We go ahead and organize it all in a table. This table might seem meaningless, like, what does this have to do with chemistry? What does this have to do with that? But it has a lot to do. This arrangement itself, it's really useful. As you move along there, as you move towards the outer side edge, you will fill up an electron shell. Once you fill it up into a complete full set, you will have to restart and come back here to start with a new electron shell that really wants to react with something. That's why group people from here and elements from here really want to react with each other. We have, well, mainly several groups. Hydrogen is a group by itself mainly because it's an anomaly. Alkali metals and the alkali earth metals. We have the bulk of the table, transition metals. Then we have, well, the semiconductors, metalloids, and nonmetals. We have the halogens and the noble gases. And finally, we have the actinides and the lanthanides. Which one do you think is the actinide? Do you think it's this, or do you think it's this? It's actually the bottom one. Why did I say actinides instead of lanthanides? I wanted to trick you, ha ha ha. Here we go, though. I'll try to explain the periodic table really quickly as well, too. Let's start with hydrogen and the alkali earth metals. Hydrogen by itself is kind of an anomaly. Most of these little guys are solids, except some of them which only last for a few seconds, but they're still solids. Hydrogen itself is a gas. It's the first element created in the universe, mainly because it's the lightest and requires the least amount of particles. 2. You only need a proton and an electron to create hydrogen. A simplicity that no one else can match at all. But if we zoom into hydrogen real quick, and usually it's put there, but some people actually go ahead and erase the whole thing and put it in a category by itself. Interestingly though, it does have similar properties towards the alkali metals. You will see why soon. A little general rule of the periodic table, when the elements are down, the elements that are down the topmost one, they usually all have similar chemical properties, mainly because they're all missing one part of their electron. Like this guy is missing 1, this guy's missing 0, it's full. This guy needs like 2 more to become full. This one needs 3, this one needs 4, this one has 5, this one has 6, this one has 7. And the magic number, because 8 is a full shell. That's why we call this 8th column the 0th shell. the column 0. By periods, though, we just call it 1, 2, 3, 4, 5, 6, 7, 8. We don't skip this whole thing. And now let's talk about the soft metals themselves, the alkali metals. Now, the alkali metals themselves have really interesting properties. One of the most interesting properties is that you can throw it into water and see it explode, and it's really fun to do so. That's one of the main reasons why they're put into fireworks so much. And the most fun element to throw into the water is sodium. Number 11. Sodium itself is really fun to throw into water because, well, unless you didn't do the right precautions, which in that case, it would just melt your face and blind you for the rest of your life if you somehow survived that. If you did take the proper precautions, you would see a really big explosion that's sparkling and really great. How do I know this? I've seen it myself. With your own eyes? No. But why do they react so quickly to water anyways? Well, these guys have a tendency to react with everything really violently, mainly because they only have 1 electron in their shell, and so they really want to give that away. Either that or they can just gain 7 electrons, but it's easier to just get 1 away than get 7. They react so violently with mostly these guys. The guys from like group 7, mainly because they need 1 electron to complete their shell. So it's not very uncommon for these guys to react quickly with these guys. And then the second column we call the alkali earth metals. It's basically the alkali metals, but in the middle we go ahead and add the word earth. Now, these guys also react with water, but not as violently. I think it's because they're a little bit more full than alkali metals, so they have less of a need to go ahead and lose their electrons. It's still easier to throw away 2 electrons and gain 6 electrons, but either way, though, they still need to react with something. They also have a tendency to react also less violently than the alkali metals. And when they react with water, they don't like just explode into the air. They're like just fizzle out and create some hydrogen cells as well too, which is really useful byproduct, mainly because this ensures that we can go ahead and create hydrogen fuel cells and hydrogen fuel plants. Otherwise, how would we be able to produce hydrogen? Next, we have the transition metals. Now, the transition metals themselves are the bulk of the table, and as you probably noticed, they are pretty much most of the table too. We skip them in the electron counting, mainly because, well, they don't react that violently, especially these guys. We have never seen them react, mainly because they're man-made and cannot last they can only last for a few seconds. Anyways, as the name suggests, they're mostly metals. All of them are solid except mercury, which is liquid at room temperature, but it can also be a solid when it's cold enough. And as you know, these are the most common elements in the entire world as well too. It's the workhouse elements. Elements such as iron has been used for centuries, and elements like tin and copper, which is like somewhere in this row, by the way, have been used to create tin and other aluminum-like cans. They're mostly malleable, and they conduct electricity a little too well. That's why they're not used in computers for conducting electricity, because if you do use it for a computer to conduct electricity, you will have a very melted computer. But what's this? What are these 2 empty spots? Well, those empty spots are for the lanthanides and the actinides. The lanthanides are supposed to go here, but, well, they can't fit, obviously. While the actinides should go in the bottom corner, but also cannot fit. They all have practical uses, and the most famous one being titanium. Then we also have these guys, the silver and the gold. Number 47 and number 79. We also have platinum, which is slightly more rare than gold. And then we have these guys. These are basically the metalloids. The metalloids themselves are like semiconductors, except they don't conduct electricity that well. They will conduct electricity, just not as well as the transition metals. And they are kind of safe enough to use in computers, but they're probably not that powerful enough to. Between the metals and the non-metals, there is this diagonal line, and that's called the semiconductors. And those semiconductors themselves are the ones that we use inside our chips. It includes silicon and surprisingly, boron. And these are really useful in conducting electricity because, well, you can use it and make sure that your device doesn't melt. And finally, we have the non-metals. None of them, with the exception of carbon, do not, I repeat, do not conduct electricity. For some reason, only carbon conducts electricity, but that's probably because of its chemical properties. I mean, why else? What other atom creates a hexagon shape? One more thing to mention, though, the elements in this vertical line, they're the only ones that actually kind of violate the rule where elements in the same period have same chemical properties, mainly because these guys have the same chemical properties. These ones don't really have that many, but these ones are the ones with their most common chemical properties. Then we have, reached to the other side of the table, we have the halogens, which are gases, and the noble gases. Most of these are found as gases, mainly because that's the only form that they take. All of those elements are highly reactive, as I mentioned earlier, mainly because they react so well with these guys. These guys really need to gain 1 electron. These guys need to lose 1 electron. Add them up, you get a total net 0, and that is the best you can do ever. Ever. Would you rather give an electron to someone who needs the electron and, well, you're full? That's probably great too. It's a win-win situation. Atoms really want to become stable. That's why they're isotopes. Stable versions of the atoms. Most of them, though, there's not much use. Except fluorine. Fluorine is inside toothpaste, and chlorine was used as a gaseous super weapon in World War One, but then they just cancelled that because they realized, the Germans and the Allies both realized that whoever set off the gas, everyone died. The very last columns, though, they're called the noble gases, so called mainly because they don't react with anything, and they would rather not touch these peasant of elements. These elements that react with each other, they're all peasants. I am noble, I do not need help from anyone. That was a very good king impression, in my opinion. And finally, we have the lanthanides and the actinides. The lanthanides and the actinides are known as the rare earths, despite the fact that they're not rare at all. Uranium is surprisingly easy to find, and you can even own it, also in very small amounts. The top row, lanthanides, it's named after the first element, lanthanum, and as you guessed, the bottom row, actinides, is named after their first element, actinium. All of the actinides are radioactive. Uranium and plutonium are the most famous versions of these radioactive elements. The lanthanides, though, they're just there mainly because they can't fit in the periodic table. And now that you are up to date with, the periodic table, you can finally understand this. This is electron arrangements. You don't really need to know them. They're just quantum mechanics. But basically, this field, inside the middle of it is the nucleus. And everywhere else, the empty space, that's where an electron might be. It's good to know that an atom is mostly empty space. Basically, if you have an entire football field, the neutron, the proton, the nucleus would be here. But the electron will be way outside here. I guess you can't see that. The electron will be way outside here. Mostly empty space, I told you. These are all just different types of orbitals as well, too. There are s orbitals, p orbitals, d orbitals, and f orbitals. But regardless, though, you don't really need to know this for the rest of the book and the rest of these series. So that's it. That's the introduction of the periodic table. I hope you guys enjoyed this episode. I hope to see you guys soon. I'll look forward to starting with you guys in the 5-minute specials. And until then, Shnan out. Peace. Bye-bye.